All right, now in this video, we'll take a look at linked lists, looking at how linked lists work, looking at how we initialize a linked list, insert items to a linked list, and also delete items from a linked list. Let's get started. What are linked lists? Linked lists are what we refer to as a linear abstract data type, because in a linked list, you have these so-called nodes or elements that point to the element after, or each node points to the next node. So there's no tree structure or a hierarchical structure. It's all linear, where each node or each element points to the next. And just to re-clarify, you have in a linked list these so-called elements known as nodes, which contain data and a reference, also known as a pointer, to the next node in the sequence. And in our syllabus, we implement linked list using arrays, which, if you have learned about linked lists elsewhere, might be a bit counterintuitive, because linked lists are supposed to be dynamically resizable. But in our syllabus, we tend to restrict linked lists to a specific size and work with arrays when we talk about linked lists, right? But don't let the previous understandings of linked lists confuse you. It's the same thing. Whatever you have understood about linked lists are potentially the same. It's just that here we use arrays to implement linked lists of fixed size. Now, linked lists, similar to stacks and queues, have two primary operations: insert, to add a new node at a specific position. Specifically, we can add nodes to the front or start of a linked list, to the middle of a linked list, wherever you want to, and at the end of a linked list. And then we learn about deletion, which is to remove a node from a specific position in the linked list as well. And this can be done through removing a node at the beginning, a node in the middle, or a node at the end. And another operation that's not a primary operation, but it's still relevant, is to find, right, where you can use it to search for linearly from the start all the way to the end for a specific node you wish to find. So those are the two primary operations, insert and delete, along with another tertiary or secondary operation called find. Now, linked lists are used in a variety of different places, but mainly they are used in dynamic memory location to allocate memory where the data size changes. Linked lists are used to represent or implement stacks, queues, and graph representations in the computer. Specifically, we call these graph representations graph adjacency representations. And linked lists are even used in hash tables or hash maps internally in memory. Linked lists are also used in music or photo galleries to browse items sequentially, if and when necessary. All right. Let's now take a look at the process of initializing linked lists. Now, to initialize a linked list, ladies and gentlemen, you first have to initialize nodes. You first have to initialize nodes, however many nodes you want. Let's imagine that we are initializing a linked list which has 4 nodes. The way you do this is you first give yourself a single node. A node, like we discussed, is composed of data and a pointer, which is the index of the next node in the linked list. Usually the first node of a linked list has an index of 0, and at the beginning it has no data. And let me actually initialize the remaining nodes as well. This next node might be at index 1, where it might have some data and a pointer. The next node after that might be at index 2 with some data and a pointer. And the node after that might be at index 3, right? The node after that might be at index 3. Now, you might be worried about why we are initializing these nodes sequentially, 0, 1, 2, 3, because if you learned about linked lists elsewhere, you might know that these nodes exist randomly throughout RAM and that they are not sequential. But the reason we initialize each of these nodes sequentially is because each node in this linked list implementation is an array element, right? So since the way that we implement linked lists in the Cambridge syllabus is using arrays, you can expect these nodes to have sequential indices. But in reality, do know that these nodes could exist randomly across RAM. So the code that we write should not take this sequential account into nature. Please keep that in mind. We do not ever do current index +1 or current index -1 when we work with linked lists. Even though they might appear sequential, they may not be sequential. So the idea of incrementing indices or decrementing indices is not at all valid for linked lists. So keep in mind, no sequential behavior should be inferred just because the indices are placed in 0, 1, 2, 3 order. That's only a byproduct of the fact that we're using an array for our linked list. So we've created 4 nodes that are currently empty, and then we connect each node to the next. How exactly do we do this? Node 0 will have a pointer with a value of 1, which indicates that this node points to the node at index 1. And then we repeat. This points to 2, 2 points to 3, and 3 doesn't point to anything. What do we do then? The last node's pointer must be sent to null. Usually, to indicate that the linked list has come to an end, we can set this to -1, which is one way of denoting null, or you could use the null set symbol, which are both valid symbols to represent null in a linked list in Cambridge. Right. And then finally, we have to create an external pointer called start pointer, which we start by setting to -1, and start pointer points to the first populated node of your linked list. Since all of our linked list nodes are currently empty, start pointer is set to -1 because there's nothing that our list contains right now. There's not a single node that is currently full. It's not populated. None of the nodes are populated. None of the nodes can be therefore considered as a starting node. So therefore, we consider start pointer as -1. Free pointer is set to 0. Free pointer points to the index or is the index of the node that the next value should be stored at. So as you can imagine, the reason why free point is 0 is because if we were to add a new value to our linked list, that new value should go to index 0 because that's the first free node of a linked list. But that's about it. In terms of initializing a linked list, you should initialize n nodes, which usually is in the form of an array. Then we connect each node to the next. We set the last node's pointer to null. We initialize start pointer to -1, and we initialize free pointer to 0. Then let's learn about how we insert nodes into a linked list. Let's start off by initializing our empty linked list as before, where we have 4 nodes in our linked list, right? 4 nodes in our linked list. Let's give each of these nodes the usual indices 1, 2, 3, and 4. And if you'd like, you can start them at 0 as well. In the early example, we started the first node's index as 0, but here we are starting the first node's index at 1. Again, it doesn't matter. You can start it at 0 or 1. That's no problem. But make sure that you point each node to the next node's index. Otherwise, the connections cannot be established during the insertion process. So we set node at index 1 to point to node at index 2, 2 to point to 3, 3 to point to 4, and 4 to point to null, which is another, which we are using the null set symbol to represent null here, but earlier we used -1. I'm just trying to show you that all of these different techniques represent the same exact thing, right? But that's about it. But I can draw arrows to represent the fact that each node is connected to the next, and our start pointer will in this case be -1 because there is no start to our linked list right now. And our free pointer will be set to the index of the first node that can have a value in our linked list. The first node that can potentially be populated in our linked list is this node right here. So we can set our free pointer to 1. So free pointer can essentially be the lower bound of your array if you're working with an array-based linked list. But really, any node that you think would be the next location that can be populated, that could be the free pointer. Usually it's the first node in your linked list. Specifically, in this case, the node at index 1. But it could also be the node at index 0 if you'd like that instead. But yeah, now it's time to insert an item to the linked list. Now, what I want you guys to understand is that right now, even though this linked list is connected, Cambridge and thereby the syllabus doesn't consider this to be an actual linked list. It considers this to be a free list. This is referred to as the free list. Basically, this is a linked list that has been pre-prepared with connections, but it's not really the true linked list yet. This just shows you what nodes are available to be provisioned to potentially insert values in the future, right? This just shows to you what space you have, which you can then allocate to your actual linked list later on. So keep in mind, this shows you all locations that you have for allocation to your linked list. In other words, it shows you the free list. It doesn't actually show you the proper linked list. But let me get to the proper linked list now. What exactly do I mean by the proper linked list? Basically, to insert an item to the linked list or to add an item to the linked list, the first step is to go to our linked list and find the node that is at position free pointer. Find the node at position free pointer. And the reason we can do this indexing is because a linked list based on our syllabus is implemented as an array. What that means is we are going to index 1 of our linked list, which is essentially this first node in our linked list. Now, that node is where our value should go. So what we'll do is we'll access the value part of that node because it contains two parts, right? It contains the value or the data part and then the pointer part. This dot value represents the notation to access just the value part of that node. And we can set our item to that location or that position or that node that free point is currently pointing to in the linked list. So let's say that the value that we're adding here is 25 and successfully we can add 25 to that location in the linked list and call it a day. But the thing is, this doesn't really complete the process because the way that Cambridge expects you to work with a linked list is you're supposed to maintain your populated list and your free list separately. That is a very, very important thing for you to understand. In Cambridge, it's very important that you understand that the free list must be separate from your populated list. Therefore, we are supposed to sever this connection. The connection you see here, this connection must be severed in light of separating this free list from the populated list. But how exactly do we sever this connection? How exactly do we break this connection apart? It's pretty simple, but you have to pay attention. Make sure that you guys are paying attention for this process. The way you sever a connection in a linked list is pretty straightforward. Once you add an item to the free pointer location of the linked list, the next thing you do is you update the free pointer to whatever the pointer of this node is, right? But before you do that, we are going to maintain a copy of our free pointer in another variable called temporary pointer. So I'm going to say temp pointer is going to be a copy of free pointer. Why temp pointer is used will make sense to you later on. So I'm going to create another variable called temp pointer, guys. and temp pointer will maintain a copy of free pointer right now, which in this case will be 2. Sorry, it'll be 1, which will be whatever free pointer's value is right now. So we maintain a copy of our free pointer. And then, like I said, we can proceed with updating free pointer to be the next free node. What is the next free node going to be? That's whatever this node is pointing to. That's the pointer of this node, the node that is currently pointed to by this yellow color arrow. That node's pointer number 2. That number 2 should be the free pointer's next value, because that's where the next node should go when we want to add another item. Position 2 is where the next item should get added. So linked list free pointer dot pointer, that is the pointer of this free node, will be what's saved as our free pointer for the next turn. So free pointer is going to become this free nodes, or rather the node that you just populated, that node's pointer should be what the new free pointer becomes. So the new value of the free pointer should be this node's pointer, which indicates that the next node to be populated is the one that this node is pointing to, which is also a free node, right? So we update our free pointer to 2, right? Free pointer changes from 1 to 2, right? So far we've updated the current node's value to be whatever item we want to save there. We've updated free pointer to be this node's pointer, the current node's pointer. And before we did that, we also created a copy of temporary pointer. We created a copy of free pointer into another variable called temporary pointer. So we currently have free pointer that is currently 2 and temp pointer that is currently 1. Now it's time to do that separation. The populated list must be separate from the free list. The next 2 steps are very crucial for this process. Step number 4. The next thing that you should do is you should basically update this node's own pointer to be the start pointer. So if I were to summarize this, linked list free pointer dot pointer should be the start pointer, should be set to start pointer. So what is the start pointer's current value, guys? That should be -1. So we update this node's pointer to -1. As a result, severing this connection as well. That is exactly what we wanted, right? This will be set to -1. And then this connection that was previously between 1 and 2 will be broken apart. That will now be broken. And once the start pointer has been used to update this node's very own pointer, the next thing we can do is we can update start pointer to be that temporary pointer that we copied free pointer into. And start pointer will therefore become whatever temp pointer is, which is 1. And that, ladies and gentlemen, says that the start of our linked list is this node, node number 1. And that has successfully updated our free list, to be this portion of the linked list. And our populated list is this portion of the linked list. This is how you insert nodes to the beginning of the linked list. Feel free to try adding another node. Feel free to try adding node number 2 and see what happens. Just to give you a quick walkthrough, if you were to add node number 2 into this linked list, the next node, let's say we were adding 36 into this linked list, 36 would be added to the free pointer's current node. So free point is pointing to node number 2. That's where the new value will go. 36 will go to node number 2. Then you'll copy the free pointer that is currently 2 to a temporary variable, which is used to update the start pointer later on. And then what we do is we update this node's very own pointer. Sorry, my bad. We take a copy of this node's very own pointer, and that becomes the new free pointer. So essentially, we update the free pointer to be the node that is pointed to by this node. This current node is node number 2. Whatever this node is pointing to, that becomes the next free pointer. Essentially, graduating our free pointer to be the next node in the free list. That way, the next time a new node comes along, we don't keep populating node number 2 again and again and again. We update the next node and the next node and the next node, keep on going. That's the idea, right? Free pointer now becomes 3. And after that's done, free pointer having updated to 3, we can then update this very pointer, the node that we just updated, this node's pointer whose value is 3, to be the start pointer. Now the start point is 1 from the previous process, right? Start point is 1, so this becomes 1 now. And what that means is that this connection severs and this node connects to the node before. And then start point is set to temporary pointer, which was the previous free pointer. Thereby start pointer becomes 2, which means that this start pointer now points to this node here. Now, what exactly did this even do? Notice how 36 now becomes our first node because that's what the start point is pointing to. And this node points to the previous node, essentially creating a chain of nodes in the opposite order. That's what inserting to the beginning does. Hopefully that makes sense to you guys. Feel free to try this out multiple times. This process, even though might seem a bit counterintuitive, is the most efficient way to insert nodes into a linked list because it's a constant time operation. Inserting nodes to the beginning of a linked list is very easy and very fast to do. But this is in contrast to insert into the end of a linked list. Imagine you had to insert to the end of a linked list, guys. Let's imagine that we had a linked list with just 3 nodes. With just 3 nodes, right? Now, let's say that these nodes have the indices 0, 1, and 2, and the values 35, 23, and 46, where each node is pointing to the next node. Pretty straightforward, right? Now, let's say we wanted to add a new node to the end of this linked list. The way we would do this is we might have to create a new node. We can get this from our free list. And what we have to then do is start at our start pointer, wherever the start point is. In this case, start pointer could be 0. Search until you get to the end of the linked list, which means search all the way from the beginning of the linked list until you reach the node whose pointer is null, and then update that node's pointer to point to the new node, and then update that node's pointer to be null, and then set this node's value to be whatever value that you want. Now, this might seem a bit easier to understand than what we learned earlier, but it's honestly a bit time consuming to the computer because of this linear search operation, right? It takes time for the computer to have to search all the way from the beginning until the end. Now, this problem can be solved if you use a doubly linked list, which is a linked list whose nodes connect to the next node as well as the previous node, which means that it's very easy to find the last node without having to search the entire linked list. But when we work with this linked list, this is known as a singly linked list, this process is quite inefficient. And finally, how do you delete a node from a linked list? Let's again imagine that we have a linked list as follows. Where each node is given an index of 0, 1, 2, and each node might have a value of 33, 45, and 56, for example, and each node might point to the node afterwards. Let's complete this diagram really quickly. Now, let's say that we wanted to delete this node right here, the node 45. How exactly do we do it? Step 1 is to search for the node that you want to delete, right? Search for the node that you want to delete. Now, that means you start at the start pointer, and slowly but incrementally, you get to the node that you want to delete, right? Now, not only should you get to the node you want to delete, you're supposed to also find the node previous to that node. So not only do you search for the node, which we will call the current node. This would be the current node in this case. We're supposed to also keep track of the previous node. Keep track of the previous node. We'll call this our prev node, PREV NODE, which in this case is node number 1, node number 0, sorry. Now, the reason we do this is because the way we delete this node is by essentially forming a short circuit from the previous node to the node afterwards, thereby essentially declassifying or dereferencing this node that we want to delete. The way we do this is by essentially going to our previous node, updating that node's pointer to point to this node's pointer. So what does that mean? We update the previous node's pointer, linked list previous node. Oh, actually, let me just keep it clear, very simple, and let me just say previous node. You update the previous node's pointer to be the current node's pointer. There you go. That's so much easier rather than using all these index notations, isn't it? You update the previous node's pointer to be the current node's pointer. The previous node's pointer is 1. That should be overwritten by the current node's pointer, which is 2. And by doing that, you're essentially creating that short circuit, connecting 0 directly to 2, skipping number 1. And upon achieving this short circuit, you have now effectively deleted this current node. But to complete things, you can also make sure that this node no longer connects to 2, because otherwise you'll have 2 connections to the final node. So the fourth step you can do is to sever this final current node connection. You can basically set the current node's pointer to null. Current node's pointer to null. When you do that, this node's pointer would become null, and that would sever this connection, making this node permanently deleted from the linked list. That is the process of deleting from a linked list. All right, guys, that concludes the process of linked lists and the way that you work with linked lists. If you have any questions, do let me know. And again, good luck for your exams.